tell you about that at the very end as well. So, before I get started, I would like to warn you a little bit. We astronomers know that stars are not alive. They are inanimate objects, but we love them so dearly that we describe their existence as, oh, they're being born, they live a life, and then they die. That's just how we describe it, basically. So, just bear with me. Also, it turns out that for astronomers, most of the matter in the universe is hydrogen and helium. There's very little else than that. I mean, when you look around here, much of what we see here is not hydrogen or helium. But in the universe as a whole, you only have about 2% of other stuff. And all that other stuff, chemists will say that, oh, you have gases, you have liquids, you have metals, and this and that. For astronomers, anything that's not hydrogen or helium is simply a metal. So if I later on talk about metals or so, and you're like, huh, why is carbon a metal? Carbon is not a metal, right? But for astronomers, that's just how we call it, and so sometimes that happens. Okay, you have to work a little bit with me. Who knows these lines? Does anybody have any idea about this text here? Where does that appear? So it's a little ominous, right? They're shorter of breath and one day closer to death. I was like, well, does anybody know? It could be, but it's a little more recent. It's pop culture. That's why it's called a pop quiz. It's Pink Floyd, In Time, 1973. It's one of those singles that was out on the album Dark Side of the Moon, which is, from an astronomical focus, actually really nice. There's this line in it that there is no dark side of the moon, and that's one of the lines. And I've always found this interesting because they catch on to something that is very, very true. The sun is the same in a relative way. When you go out today and you look at the sun, it's going to be exactly the same sun that's going to be there tomorrow, and in 100 years, and in 1,000 years. The sun doesn't really change. It has been providing us with that enormous amount of energy for billions of years, and yet it does not change. It's kind of weird. When we look at the sun stays the way that it is. It doesn't shrink. It doesn't expand. It is in that shape that it is right now, and it has that size, and it keeps that size. That's called, astronomers like to call it hydrostatic equilibrium. It's basically, you can treat the sun like any gas, like a fluid. That's why it's called hydrostatic equilibrium. Well, in order to be in equilibrium, two things need to happen. The sun is massive. It has a lot of mass. All of that mass is attracted and would like to compress the sun and make it all fall together. So why doesn't the sun just shrink? Because there's all this gravity that should pull it together. Well, because there's also pressure. Pressure works in the opposite direction. And it's that balance, the delicate balance between gravity and pressure. And that's the struggle for the life of a star. A star always wants to balance that. For its whole normal life, the star needs to achieve this equilibrium. So how does that work? At every position inside the sun, it turns out that the gravity pulling in and the pressure, gas pressure, pushing out, are completely balanced. It's surprising how far-reaching of a consequence this has. It's a very simple observation. The sun does not change its shape, and that allows us to figure out that the sun must be very hot because of that equilibrium. So imagine we take a little slab of the sun, so we're somewhere inside the sun, there's all this stuff above it, and therefore there's a lot of pressure pushing from the top. There's also the weight of that slab, and these two forces try to push that slab down. So normally, that slab would go down towards the center of the sun. But we've just learned, no, it doesn't do that. Because there's also the pressure from the gases that are below. And that pressure must be higher, because it needs to equal the pressure from above and that additional weight. And so you can calculate that, the deeper down you go in the sun, the higher and higher and higher the pressure is going to be. It's the same thing that you experience when you dive in a pool. It's exactly the same principle. You remember it, when you go down, already a meter down, your ears start hurting, and if you're 10 meters down, you've added 1 atmospheric pressure, simply because of that principle, because the pool is the same thing. A standing pool of water does not sink to the bottom, and therefore there must be hydrostatic equilibrium. Now, when you increase the pressure, the deeper down you go, you can calculate that, well, it's a really big object, our sun, and you go deeper and deeper and deeper. Gases then also react in the way that the higher the pressure becomes, the higher the temperature becomes. So we immediately realize that, the sun is not shrinking, therefore it must be hot inside. And we can calculate it must be very, 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 very hot because it's so large. The second fact that we know about the sun being the same in a relative way is the sun keeps the same temperature all the time. Well, here on Earth, sometimes the sun is clouded out or so, and in the summer it's warmer, but that has nothing to do with the sun, that has to do with the seasons here on Earth. The sun itself always has the same temperature, and it has been keeping that temperature for a very, very long time. But that's odd, because you can see the sun, right? What does that mean? When we look at the sun, we see a lot of sunlight coming to us. What is sunlight? Sunlight is energy. Energy is leaving the sun. Normally, you would therefore expect that the sun is cooling down. If you take a hot stove and leave it, it will cool down over a while. It gives you heat, or if you have a fire or something, it gives you heat, but that heat is taken away, and therefore that thing that causes the heat is cooling down. The sun doesn't do that. The sun stays in the same temperature all the time. How does the sun do that? Well, somehow the sun must generate all that energy. So deep inside the sun, there must be some mechanism that makes energy. And then that energy is going to get to the surface of the sun, and from there it escapes into space, and that's why we can see the sun. And that needs to be finely balanced as well, because otherwise the sun would be heating up or cooling down. And the sun hasn't done that at all. We'll come to that in a second. So how can we transport that energy that is made deep in the core of the sun out so that it can leave the sun? It must come from the deep core, and then that energy needs to get out somehow. There are a couple of ways you can do this. The sun is a gas, mostly hydrogen and helium. Therefore, the heat conduction doesn't work very well. We all know that, right? If you want to heat a room, the most inefficient way to do it is by heating up the air. That doesn't really do the trick. That's why we spend so much energy trying to do that, and you open the window and all that heat goes out and say, So gases are not very good, the conduction. But convection works really nicely. What is convection? It's a circulation of fluids. So I'll talk about that in a second. And then you can also do this by creating light particles, photons. They carry a lot of energy, and that energy is then transported wherever those photons go. So here's convection. You all know convection. If you've ever been using some tool to heat up water, you put it on the stovetop maybe, or you have an electrical current going through here, and the water will become hot at the bottom where the flame is, and then this hot water is less dense and rises, forms these bubbles, and that's why when you start putting on your heat on the stove, that's when those bubbles form. And that's when the water is boiling and you realize, now it's time to cook and put the food in because now it's really, really hot. And that is convection. On the surface, the water then cools down and sinks down, and that whole cycle can begin again. So that's called convection. And that actually does happen on the surface of the sun. When you look with a big telescope and you zoom in, the sun has all these granular structures, billions and billions of these things that are about the size of the Earth. So one of these is you're zooming in a lot, and this is about the size of the Earth. This is where hot gas comes out. It's a little bit brighter, and then it cools down, and therefore it's not quite so bright, and there's this whole, it's like a cauldron that's bubbling. For us, when we look at the sun seems to be just fine, not doing anything. It's like a hot cauldron that is bubbling all the time. And we've measured that. We can measure how fast the stuff comes up or sinks down, so that's an image of that. So the second way that you can generate that energy and then transport that energy is by simply using light, and that is what's happening in the center of the sun. However, the problem for any light particle inside the sun is that, well, unlike space, when it reaches the surface of the sun, it just zooms off because there's nothing there to impede it. But all that stuff, it's very, very dense, and any kind of light particle, a photon, that wants to get out, bumps into that stuff and gets deflected. And it gets deflected in a random motion. It just bounces around, and that is called a random walk. So instead of going out in a straight line, so normally when you think, okay, I make light, like with this laser, and then it zooms off in a straight line, but that is not what's happening. What's happening is that it bumps into all that stuff, and after a while, however, it gets closer to the surface, and that's called a random walk, because at each bump it goes into a random direction, and after a while it reaches the surface. And then once it reaches the surface, woof, it goes off. This whole process takes about 1,000 years. So light that is being made before it can leave the sun is on average about 1,000 years old. So think about this. Next time you look at the sun, those photons that your eyes receive, they were made 1,000 years ago. So they're not present-day energy generation. It's about 1,000 years ago that they were made. This is sometimes also called the drunkard's walk, because it reminds people that, well, you've been in the bar, you've had a little bit too much, and each step that you take is basically a random step, and that means that it takes you a lot longer to get home, and that's what happens with the photons there as well. So I've already told you that the sun has been doing its thing, shining and not changing shape, for a very, very, very long time. We know that because we find evidence of life forms, simple bacteria that have been growing on the Earth, that are at least 4.2 billion years old. In order for these to live, there must have been liquid water on our planet. And that must mean that the sun must have been shining roughly with its luminosity that it has right now, because otherwise it would be too cold. It also cannot be that it was too hot, so there's a fine range that allows for life to happen, and that life has been around for 4.2 billion years. So the sun has been shining with that much energy for an enormous amount of length. You can calculate how much energy you need. And that's when physicists, when they first learned about the age of the planet, they were scratching their heads and said, wait a minute, this is really strange. How can it be that the sun can generate that much energy? What is powering the sun? So in the 18th century, when people were basically using fuel like coal, or they were starting to use oil, you can simply calculate, well, if the whole sun is made out of coal or oil, and you burn that, you can do that. But you're burning an enormous amount of oil and coal, and you would run out of that. The sun would basically run out of about 10,000 years. Clearly, the sun is not using oil and coal. There must be some other process that cannot be chemical. Kelvin and Helmholtz, they discovered, there's a clever method. When you shrink an object, there's an enormous amount of gravitational energy in the sun because it's so massive and so large. And when you shrink that just a little bit, you gain a lot of energy. Maybe that's what's fueling the sun. But you can calculate that, and that gives you, well, much longer. It's like, okay, problem not solved at all. This is 25 million years. It's not enough at all. So there must be another process that is giving us all that energy. Furthermore, that thing doesn't work because we've just learned that the sun is not shrinking. So therefore, this gravitational stuff doesn't happen. So what's the solution? Well, you've heard it maybe last time. It always comes back to Albert Einstein. Albert Einstein, E equals mc squared. That solves apparently everything. Literally what this means is that you can turn mass into energy. This is the famous energy and mass equivalent. Out of a tiny little amount of mass, you get an enormous amount of energy because you're multiplying it with the speed of light squared. The speed of light squared is an enormously large number, and that gives you an enormous amount of energy. So all that you need to do is you need to be basically the ultimate alchemist. You need to turn elements into each other. That's what alchemists have been dreaming of all the time, and the sun does it for us. It takes hydrogen and turns 4 hydrogen nuclei into a helium nucleus. And when you weigh those two, when you put them on the scale, you will realize that, oops, in that process, you're losing just a little bit of mass. What do you mean losing mass? Yeah, you've lost mass and turned that mass into energy. This, despite the fact that this is so little, as you can see here, 10 to the negative 27 kilograms, that's nothing, right? It's a tiny little amount. But multiplying that with the speed of light squared and then having bazillions of these atoms do that, you can get an enormous amount of energy out there. So that's why we all wanted to learn how to do this here on Earth. If we could do that, hydrogen is very, very prevalent. Take a bucket of water, you separate the oxygen and the hydrogen, and you have lots of hydrogen. If you take 1 kilogram of hydrogen, it's the equivalent of 20,000 metric tons of coal or oil. So in the end, you still need a lot. So these are these astronomically large numbers. Every single second, the sun is burning 600 million metric tons of hydrogen and is converting it into helium. While I'm doing this, every single snap of my finger, we turn 600 million metric tons of hydrogen into helium. And that makes it so nice and bright outside today. So that is the solution to the problem, although, well, there's still a big problem. How does the sun do that? Because it turns out that when you take hydrogen, the last thing that these hydrogen nuclei want to do is get together to form helium. Why would they do that? Because, remember, they're positively charged. They repel each other with an enormous force. And that's why this can only work deep inside the core of the sun, because you need to do what's called thermonuclear fusion. We have made this here on Earth as well. So we created bombs that do that. And those bombs, basically a thermonuclear bomb works in such a way that you take hydrogen and you make it implode by having a normal nuclear fission bomb around it. And that creates then the conditions where you can have what is called thermonuclear fusion. And it's what the word says. Fusion is you're putting things together. So you're taking hydrogen and you're forming something else. This is different than splitting. So uranium, when we use uranium, we split it up, and that gives us energy. This is putting things together. So that's why it's called fusion. It's called nuclear fusion because you're dealing with nuclei, the cores of atoms. And thermo because you need an enormous amount of energy to do that, and that means you need to be very, very hot. The good thing for us is that we've just learned that, oh, the sun is very hot in its center. So And that leads to this idea that, oh, all that you need to do, I'm not going to bore you, this is basically what is called the proton-proton chain, and that is what the sun is doing for a couple of billion years already. Deep inside, it puts together these positively charged particles, and they can only come together because they're moving around so fast. That is what temperature is. When you are at a high temperature, at the inside of the sun, it's very dense, so there are many, many, many of these things, protons, and they're zooming around with an enormously high speed, and that's when they can sometimes get together and form helium. And in that process, you gain an enormous amount of energy. That's, as you can see, this is what's literally happening inside the sun, and that's awesome. That's great. This means the sun is stable, as we've just seen. It's the same in a relative way. It doesn't change. It has reached a happy place. And this is when stars live their happy life. They have solved a big problem. They know how to fight gravity. They create that pressure. And they know how to create energy because it's hot enough in them to turn hydrogen into helium. If anything changes, they have invented basically the ultimate thermostat. If it turns out that it gets a little bit hotter, because the sun is shrinking a little bit, you would increase the temperature, but once you make it hotter, you're running this oven at a much higher rate. It's like you're turning on your oven to overdrive, and therefore you're generating an enormous amount of energy that will lead to heating the thing up, and that would make it expand. So it's a negative feedback loop. Whatever you do to change the size or the temperature of the sun, that mechanism drives you back. It's like you have in your house that thermostat that you said, oh, if it's a little bit too hot in the house, let's put the air conditioning on, and then it cools. And after a while you say, this is now too cold, let's stop the air conditioning from the outside, the heat heats the house up again. And so you're maintaining a balance, and the sun does this extremely well. But that also means that part of the life of the sun is very boring because it's in equilibrium. Nothing happens. It's actually really hard to tell how old, for example, the sun is because it's in this equilibrium. It doesn't change. How do you tell how old something is if it doesn't change? If I show you a baby picture of me and a picture when I was 15 and a picture of me now, you will easily be able to tell which one is which, right? Because I am changing. The sun doesn't. The sun is in this boring equilibrium and nothing happens. But why is nothing happening? Well, because the sun has this energy creation, but that relies on turning hydrogen into helium. At some point of time, there will be no hydrogen anymore. You have turned all your helium into, all your hydrogen into helium. Now what? Like, okay, well, if my car runs out of energy, electric car, I just plug it in, or I go to a fuel station and I refuel because I have external sources for that fuel. The sun doesn't. Once the sun has eaten up all its hydrogen, blop, what now? And that's when the real problems start to happen for stars. So you would think that, okay, well, now it cannot generate that energy anymore. It will cool down, and therefore the pressure will go down, and then gravity wins that whole battle. So the star's life is this whole struggle between gravity and pressure. The pressure source is now gone, and whoop, that thing will shrink. But that's not at all what's going to happen. It's quite interesting how stars react to their energy crisis problem. So it turns out that, yes, inside, deep in the core, there is now no pressure source anymore, and that means that the core is starting to shrink. But it turns out that the outside of the star, the outer layers of the star, they do something very different. And what exactly happens depends on how massive that star is. Stars like our own sun, with one mass, one solar mass, up to about 4 solar masses. They undergo this pathway that we're going to talk about in a few minutes, and will end up as what are called white dwarfs, going through a giant phase and a planetary nebula phase. More dramatically, stars that are much more massive than our own sun at the beginning, over time, they will turn into supergiants, and then they will explode in these giant catastrophes that are called supernovae. They will leave behind either neutron stars or black holes. That's a whole topic in itself. We'll maybe talk about this at some other time, but I'm going to focus later on the supernovae. So what happens with our sun? So we've just learned that it has run out of hydrogen in its core. That's a problem. Pressure is not there anymore. The core starts to shrink. But once you squeeze together a gas, it starts heating up. If you tried this, if you take a pump, an air pump, and you're holding your thumb there and you're pumping it like that, that can hurt a lot because you're compressing the gas, and that can get very warm very quickly. Same thing here. You squeeze something together, a gas together, and that heats up the gas. So now the gas deep in the core is heating up, but the core, of course, is in contact with all that other stuff that's around. And there's still a lot of hydrogen around. And that now turns on as well. All of a sudden, you reach temperatures in places of the star where you can now burn hydrogen again, where it wasn't possible beforehand. And so now all of a sudden you create a lot more energy because there's a lot more stuff in the outer layers that hasn't been touched yet. And that means that the star is going to swell up. So the inside is shrinking, but the outside is swelling up a lot. And that also means that the outer layers, when it's expanding, are becoming a little bit cooler. Again, gas expanding means it cools down, and you end up what is called a red giant. It's a giant because it's humongous compared to what it is now, and it's red because it's cooler. Once you cool something down, it's not glowing as nicely orangish, yellowish as now, but it will turn an angry red, basically. And that's why we call this thing a red giant. So that will happen in about 5 billion years. You might think that, okay, well, this is very dramatic. It blows up the sun to about the size of the orbit of the Earth. So it will definitely swallow Mercury and Venus. It's not exactly clear. It depends a little bit on where the metals are and how many metals there are, whether it's going to reach the Earth or not. This is a giant thing now. It's about 200 times in radius larger than it was before. And it's about 3,000 times more luminous. At that moment, you have to be away from Earth because we get singed completely. We will lose our atmosphere, and it's the ultimate catastrophe for life on Earth, basically. At that moment, we need to get away. There is a chance that we could get to the outer planets, but that only lasts for a couple of million years as well. And then the old age is set in for stars, and finally the core does the same thing again. It heats up, and at some point of time, it realizes that, oh, I'm hot enough that I can now use all that helium. In order to bunch helium together and create carbon and oxygen in the process, you need even higher temperatures. Those higher temperatures are reached at some point of time, and that means you're going through another giant phase. And at one point of time, the star becomes very unstable. Because the helium burning is sensitive to all sorts of tiny little changes in the temperature, and that literally means that there are now thermal pulses running through that star, and at some point of time there is enough pressure that pushes away that outer envelope, and about 40% of the mass of the sun will just be pushed away into space. That's surprisingly fast. It only takes about 100,000 years. For astronomers, that's a blink of an eye. And now you have two things. You have that outer envelope that's expanding into space, and you have that little core. That core cannot do anything. The core never gets hot enough to do anything, and it basically just sits there until it shrinks, and then it finds a mechanism to stabilize itself. It's called degenerate pressure of electrons. It's a physics thing that we don't need to really worry about here, but it finds its happy equilibrium again, but it doesn't create any energy anymore, and therefore it's now cooling down. This phase is called, very confusingly, planetary nebula phase. It has nothing whatsoever to do with planets at all. These are the dying embers of a star that once used to be like the sun and is now not anymore. It is called planetary nebula because in the earliest pictures, when people discovered these on photographic plates, these places where this happens, they look a little bit like planets. So a planet would look in a photograph like this, would look very similar to this. And people didn't understand what they were seeing until they figured out what was going on, and then it was too late because it's not, it's totally misleading. People think, oh, it has something to do with planets. No, it has nothing to do with planets whatsoever. What it is a hot core of a star that used to be like the sun, but has ejected all of that stuff around it, and that stuff then drifts into space, driven by that wind that comes off from that hot core, and it forms these large shells. Although it turns out that sometimes these are some of the most beautiful objects. You can see some of those planetary nebulae that I'll show you in a second, even with the small telescopes like this. And it's super nice sometimes to just look at these. Aesthetically, they're some of the most beautiful things that you can see with even small telescopes, because sometimes that material, well, space is not totally empty. Sometimes there's stuff around it, and then it runs into things, and sometimes you see these really, really interesting shapes where it interacts with all the stuff that's around it, and it's ionized in different colors. And so this is the famous Eskimo Nebula, because it looks like an Eskimo with a parka fur here. And so many of the most famous objects that you see in these textbooks or so, they are planetary nebula because they look just very, very beautiful. But for the sun itself, that's the end. It goes out with a whimper. It's kind of anticlimactic in some sense. It now is the ashes of an object that used to be so bright. It's now called a white dwarf because it shrinks to about the size of the Earth. In volume, that's about by a factor of 1 million. So it's 1 million times smaller. Initially, it's hot. Therefore, it gives us light in all the wavelengths with basically the same intensity, and we perceive this to be white. That's why these things are called white dwarfs. The white dwarf doesn't do anything anymore, but it still shines initially, thereby losing energy and therefore cooling down. At some point of time, it then becomes dimmer and dimmer and dimmer and dimmer, and then it fades away. At that moment, I would not like to be on Earth anymore because the Earth has been singed. All the atmosphere is gone. All the liquid water is gone during the red giant phase. We are now bombarded by objects again because we can't defend ourselves with an atmosphere, lots of craters. And that thing here that looks like a tiny little star is our old sun. It has a luminosity that's about 10,000 times less than it is now, and it will be stone cold here on Earth. So not a good place to be. What happens when stars are more massive? Then a whole different set of drama is going to take place. It turns out that once stars are bigger in the core than about 1.3 solar masses, they cannot stabilize themselves so easily, and they are starting to contract in the core more and more and more, and the core reaches very high temperatures. And in the end, you end up with something that looks a little bit like an onion. It's a very strange object called a supergiant. And those things are really supergiants. So now those things, they can be larger than something that would be the size of the orbit of Jupiter. So that's another factor of 5 in size. So these things are real beasts. That's why they're called supergiants. But all the drama happens right smack in the middle in a region that's about the size of the Earth. That is where you have all these shells where successively you start going from hydrogen to helium, from helium to carbon, because the temperatures are now high enough, you can do all of that stuff. and you go from carbon to neon, neon to oxygen, silicon, and what the star is doing here is basically the ultimate junkie. The star has a massive problem. It needs some energy. It needs to get energy all the time because otherwise it will collapse. It needs to create all that energy. Hydrogen, turning that into helium, is very efficient. Therefore, this can last for a long time. But once you run out of the hydrogen and you now only have helium, that helium into carbon is not quite as good. It doesn't give you as much oomph. Likewise, from carbon to neon, and so on and so forth. And so the drugs that the sun is using get successively weaker and weaker and weaker, and it runs out of fuel faster and faster and faster. The hydrogen lasts for about 50 million years. So those stars are also very short-lived compared to our own sun. And it turns out that the last stage, going from silicon to iron, basically, that saves the star only by 1 day. As I said, it's now frantically trying to find any kind of solution to that big problem, and then it runs out of solutions. Because at some point of time, when you reach iron, so you've successfully done everything from hydrogen all the way up to iron, well, now iron is problematic because you cannot fuse it into anything and gain energy. If you try to put together iron and build something more than iron, you actually need energy. You don't gain energy anymore. That's why we use, so as you can see, this curve goes down here. This is called the binding energy. And that's why we use the opposite process when we are splitting the nucleus to gain energy by fission. Because now making smaller things out of bigger things gives you energy. But the star doesn't have any uranium or anything. It has turned everything basically now in its core into iron, and then it's stuck. It cannot find anything anymore. And now a big catastrophe is about to happen. Unlike the sun that goes out with this gentle process, this star is going to explode, and it's going to be a really, really violent explosion. It's the biggest explosion that we know from mankind. And it can be explained very easily when you think about it. So what's happening is that everything in the core is made out of iron. The gravity of all that stuff is squeezing it together, and you don't have any means of generating pressure. So everything collapses. It's basically in free fall. All of that iron and all of that other stuff starts collapsing. It's an implosion. It goes from about the size of the Earth to something that's much, much, much smaller. And it just is free fall. The free fall is fastest the closer you are to the center, and all that stuff that's around it is raining down afterwards. But now something strange happens. Once you squeeze together all these nuclei, physicists tell us that at some point of time, they all turn into neutrons. You squeeze them so hard that instead of having iron and stuff like that, you turn all of that into neutrons. And that suddenly brings a stop, because now you're squeezing everything together to the density of an atomic nucleus, and all of a sudden, there's a form of pressure. It's again quantum mechanics. Don't go into the details here, but all of a sudden, all of that material finds again an equilibrium and stops shrinking, but only in the core. All of a sudden, you have a solid surface again, and all of that other stuff is still collapsing onto this solid surface now. What happens when you bump onto a solid surface? Well, you bounce, all right? Some of that material that is collapsing down, now suddenly there is a floor again, and that stuff bounces back. It's kind of harmless, right? It's not very impressive. But what you have to understand is that there's lots of material that comes raining down. And the material that's further down is accelerating faster because the force of gravity is stronger there. And that means that you have layer upon layer upon layer that is falling down, and some of that stuff is coming up. And that gives it a kick. And that is surprisingly violent. Just like myself here. The microphone. So here's this demonstration. You've seen that the tennis ball doesn't bounce very much. The basketball it bounces a little bit better. That's why we play basketball that way. But look at this. Once I'm going to let them fall, and they are basically falling together, look what that the tennis ball is going to do. I've actually destroyed sometimes lamb, so Zach, we need to be careful here. So this is a really cool demonstration of a supernova explosion. Imagine this is the mass of a whole star that is slamming down, and then this happens. We need to do this again. It's always the problem. I'll start it from a lower here. So, you see, this is a lot more violent, and I've done this in lecture halls at about 3 times the size, and it usually hits the ceiling. It's really, if you do it well, it's really, really nice, and it tells you that, oh, instead, you would think that, oh, gravity is squeezing that star now together. But exactly the opposite is happening. You have a giant explosion. That explosion rips apart the star completely. It's actually being helped by all the neutrons that are in there. They actually emanate neutrinos, and we'll talk about this in a second. So that is what's happening. So you have this iron core that rapidly shrinks, turns into a neutron star, basically, and now everything bounces off of that, and that rips apart this giant star and makes it extremely bright. These are explosions that you sometimes can see with the naked eye. Suddenly a new star appears, and it stays very, very bright. It puts out, sometimes the most massive ones, they put out for a brief period as much light as all of the other stars in a galaxy at the same time. So for about a couple of weeks, and then it fades away. So this happened, the last time that it happened and we could actually see this and observe this very, very nearby, was in 1987. It's called 1987A. Astronomers labeled those supernovae with A, B, C, and D. So that was the first one in 1987. When you look at pictures that we've taken of that area of the sky before the star exploded, yeah, there is an ominously bright star here, but nothing really like this. This is a stellar explosion that turns that star about 1 billion times brighter than before. And then, well, all of that material gets ejected, and just like with this planetary nebula, but now on a much, 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 much bigger scale, it moves and then runs sometimes into other stuff and forms these strange geometric shapes. And a couple of years later already, these rings, and nowadays they're much larger already. So that's what's happening here. It turns out what's interesting is that we think of these supernovae as these bright dots in the sky that give us all this normal light. It turns out that more than 99% of all that energy comes in the form of really strange particles called neutrinos. They carry away all of that energy. They actually help making that explosion. And so what we see here are only the little tiny remnants of about 1% of the energy. Unfortunately for us, or fortunately for us, most supernovae are hidden from us because the light that tries to get to us is usually in regions where there's a lot of star formation, these massive stars. have been born relatively recently, and whenever you have this star formation, there's lots of dust around, and that dust usually swallows all that light. So we do know of a few areas, however, special areas in the sky where we can see the remnants of these. There's one very famous one that was observed by the Chinese as a guest star in 1054. It exploded, and nowadays it looks like this. It's called the Crab Nebula. There's lots of activity going on. There's probably a neutron star at the center here, and as I said, the Chinese noticed this. You could see this at broad daylight. So for a couple of weeks, people would be out there, and it was basically half as bright as the moon. And like, whoa, what's that thing? And then it vanishes after a while, it fades away. Interestingly enough, you would think that if you see something for a couple of months, China being in the northern hemisphere, nobody in Europe has reported this. There's no track record of that. It's one of the mysteries of astronomy and history. You would think that in 1054, there must have been some people who looked at the sky in Europe and were like, that's odd, and then write it down. But there's no written evidence for this in Europe. Whereas in China, this was well observed by many, many different people and well described. So almost at the end, I told you these explosions are bad. They release a lot of energy. You don't want to be near them. So the good news for us is that in our close vicinity, there are no stars that are going to do that. Those stars, those supergiants, they're really, really bright, and we can see them over very, very large distances. And in our immediate vicinity, there is no such star, so we don't need to worry about this. But hypothetically, remember when you watch Star Wars, they built the evil guys, they built this Death Star machine. Actually, that's the whole theme of the movies, right? They always build, it's always the same thing. I've always wondered, why it didn't work the first time? Why did you try it again? No, but so what do you think? In a normal supernova explosion, how much energy do you have compared to a Death Star? The Death Star, remember, the first incarnation of the Death Star can destroy a planet, and they get a little bit more powerful as the series goes on. But what do you think? We have a supernova explosion. Could that destroy a small moon? Is there enough energy to maybe even rip apart a small planet like Mercury? Or could we actually destroy a little bit? Could we wreak a little more havoc and destroy about 10 planets? What do you think? Nah, that's crazy, right? You cannot destroy a thing like the Earth, right? So which one do you think it is? It turns out, yeah, none of the above. There is way, way, way more energy in there. The gravitational binding energy of an Earth-sized planet is about 10 to the 32 joule. In a typical energy release of a supernova, you have 10 to the 12 times that. That's 1,000 billion times more energy. If you could channel that energy into various planets, you could destroy, with one of those supernova explosions, you could completely rip apart 1,000 billion planets like our own Earth. That would be the ultimate weapon. The good thing for us is that obviously all that energy is not directed anywhere, it just goes out somewhere and it's dispersed in space. And so, but that is the amount of energy. So these things are massive explosions. These are the largest explosions that we know of as mankind. I mean, we always said, oh yeah, we've got megaton thermonuclear bombs that could wipe out the whole continent. Forget about that. You can destroy 1,000 billion planets like the Earth with that supernova explosion. And they pop out so in our galaxy, the estimate is that it's about every 100 to 200 years you have one of those explosions. And there's an enormous amount of energy. But here comes the fun thing. You don't need to worry about that energy output because they are usually so far away that we don't need to worry about that. If we happen to live in an area that is a little more violent near the center of our galaxy or in star-forming regions, the situation would be a little bit different because much of that energy also comes out in forms of X-rays and that's not so good. So you want to be as far away as possible. Sometimes it pays off to live in relatively calm neighborhoods where these things don't happen all the time. But what's really important is that, remember that graph that I showed you when you want to fuse something together? And once you reach iron, there's no way that you can fuse stuff together and gain energy. If you want to make anything in the periodic table that comes roughly after iron, that has to be made in these explosions because you need energy. And that is where you get an enormous amount of energy. So all of these elements that you see here are made during those explosions. If these explosions didn't happen, those elements wouldn't be made in the universe. So next time you look at your wedding band and like, oh, gold. That gold, all of the gold and the platinum as well, that we have here on Earth was once in a supermassive star. Well, it wasn't. It was once material of a supermassive star that then exploded, and in that explosion, it created all of that. Gold, platinum, anything that has this orangish color here, we owe to those supernova explosions. So that's kind of really, really interesting to wrap your head around. Stars can live a long life once they find out how thermonuclear fusion works, because that regulates them. So they stay stable for a long, long, long time. However, when they run out of fuel, then all crazy stuff starts to happen. And what remains are also crazy objects. So at some point of time, we'll have another talk about neutron stars and black holes and white dwarfs. The corpses of those stars are also interesting things in themselves. But that's basically the takeaway point, that these are giant explosions. And it's interesting that gravity works in a completely different way than you would naively expect, right? You would think that, oh, star cannot help against its gravitational collapse anymore, and yet it leads to these big explosions in the end. So it's always kind of fascinating to me. Thank you. And if you have any questions, don't hesitate to ask. There is no such thing as a silly question or so, because as you see, sometimes stuff happens completely counterintuitively, and therefore I always encourage questions.
Okay, so I'm really intrigued by your point that it's hard to tell how old our sun is. How is it that we know that Betelgeuse is like close to the end? Like, how do we actually do those dates?
So yeah, that's a good question. So the question was, I'll repeat it. So it is very hard for us to pinpoint exactly how old the sun is. I mean, there are certain models that kind of tell us, it must be about that age because with the metal content that it has a luminosity that's right now a little bit higher than it used to be at the very beginning. So there are indicators, but they're not very good indicators. When it comes to Betelgeuse or Betelgeuse, it's this massive star that is in the phase that we just talked about, where it's probably very close to that giant explosion, but frankly, we don't know how close it is. It could be 1,000 years, it could be another 500,000 years. For astronomers, these are very short time periods, and so we don't know. Part of it is because the physics, so the physics gets very complicated in detail then. I mean, I told the story, like, okay, well, this is what happens. We don't exactly know. For the longest time, it turns out the models that theoretical physicists and astronomers ran, trying to understand why do these stars actually explode, they didn't explode. In the computer simulations, they failed to explode. There was this bounce, but that basically disrupted the star a little bit, but then it stopped again, and then it fell back together in the computer models. But in reality, we see them exploding all the time. So it was a big problem. I think that has been solved now, but we cannot really tell precisely because it depends on a couple of factors and possibly also on local circumstances. So, therefore, when they say, oh, it's about to explode, well, that could mean, yeah, tomorrow, or it could mean in 50,000 years. So it's unfortunately the nature of the game. I mean, once it does, it's always this really strange thing in astronomy that when things, so for most of the time, nothing happens because things are generally in equilibrium. But once you run out of an equilibrium, then stuff happens rather quickly, and sometimes then you go from, oh, the star is sitting there for billions of years, and now everything happens within a day. And I go, oh, that's a little rapid. so it's sometimes that's very hard then to basically even predict. But yeah, all of these things when they say, oh, it's about to happen, yeah, I'll take this with a.
So I haven't been keeping up with it, but I heard there was a nova that's coming around soon.
Yes, so there are different, yeah, that's a good question actually. So why is that thing called a supernova? Because there are also processes that are called a nova. Both of them, the Latin word means a new star or a super new star. The super refers to the fact that these are giant explosions of these massive stars. A nova is a different thing that can happen when you have pairs of stars. So most stars actually, unlike our own sun doesn't have a companion. It's running through life solo. Most stars are binary stars. And those binary stars, they do the same thing. They live their lives, and at some point of time, they turn into other stuff. And once one of the two binary stars has turned into this white dwarf, sometimes what then happens is that the other star has not yet done its whole business of living its life because it's not as massive, but it will do so at some point of time, and then it swells up and becomes a red giant. And that red giant may sometimes get so close to that white dwarf that some material can cross between the two. Normally they're so far apart from each other that nothing happens, but sometimes at the end stages, hydrogen can then get on top of that white dwarf. And once you accumulate enough hydrogen, all of a sudden you're running fusion again, and that star becomes very bright for a while until it burns off all of that hydrogen, and then it gets dimmer again. It is not quite as violent as this explosion, but it's noticeable, and that's why it's called a nova. And that has happened many, many times. We've seen many of these, and it's weird because you have an area of the sky, you look at it for years and years and years, and there's nothing. And all of a sudden, whoop, there's a bright star. Not super bright, and it's not an explosion, but it's bright, a bright object, and then it fades again. And then maybe 50 years later, it does the same thing. It's like, oh, that's weird. And so this is what a nova is. And we think that yeah, there are many places where we are observing this, where you can literally see that there's this mass transfer, and that will sooner or later lead to this brightening of the star again. So yeah, the nomenclature is always confusing. Nova, supernova, these are two different beasts, basically. Yeah.
Can you define luminosity for me again?
Oh yes. So that's a very good question, because it turns out that in our everyday language we throw these words around, and what does it mean? So the luminosity of an object, like a light bulb, is how much energy that light bulb gives you in total. That's why when you go to the store, it says 100 watts, because that's what the light bulb does. Whether you screw it in over here or half a mile away or over there, that light bulb will always give you 100 watts. That is the total amount of energy that you get per time. But of course, I take that 100-watt light bulb and I hold it right in front of my face, I'm like, oh, this is bright. It appears very bright to me, and that's the key word, it appears. But if I take that same light bulb that has the same luminosity, if it's now across the room, I can easily look at it because it appears to be not so bright anymore. So the brightness depends on how far away you are from an object. So stars, when we measure them as astronomers, well, they all appear to have different brightnesses. Why? Well, some stars are tiny little things. They don't give you a lot of energy. They're not very luminous. But some stars are very, very luminous, but they're really, really far away. And therefore, they appear not to be so bright as well. So that's the difference between what you measure is brightness, what it appears to you. But what we want to know is, well, how much energy does it really give us in total? In order to do that, those two things hang together, of course. Once you measure how bright something is, and you know how far away it is, you can then calculate how luminous it is. But you need to know the distance, and that is always the big problem in astronomy. It's very easy to measure how bright something is. You just hold your phone or your telescope there, and you count how many photons you get. But knowing how far away something is super difficult. So, and that's a good question. In our everyday language, we sometimes, oh yeah, something is bright or something is luminous. Same thing, right? But that's the difference.
If we know that we're a remnant of a supernova because of all the elements that we have here on Earth, do we know anything about the history of the supernova? Did it make our whole galaxy, or is there any remnant of it left?
Yeah, so in our galaxy, as I said, so let's see, I can probably... we know of a couple of dozen of these types of things, and we can estimate that because we know that we can estimate how often that should be happening, because we know only massive stars explode like that. And massive stars are very bright, so we can count them easily. And we know basically how rare they are, and therefore we can calculate, oh, it should be happening every 100 years or so that we see one of those explosions. Yeah, sometimes we can figure out from that explosion where it must have been. So in this case, when it's spherical, you can see that, well, it must be right there smack at the center. Sometimes when it runs again into gas around it, then these become very much more complicated, and it's hard to see where exactly it exploded. Yeah, and then we can retrace basically how much energy was deposited into the surrounding media and how much mass that was, and so yeah, we can trace it back quite a bit by analyzing these remnants. And some of these remnants are again very, very beautiful objects in themselves. So they're very famous, many of them. So amateur astronomers, they like to look for them because they give you something to hold on to. It's not like, I mean, stars are just little dots, right? They're boring. After a while, you've seen many stars through a telescope. But these are fascinatingly shaped objects, and they all glow in different colors. And if you search on the internet and just a sampler, or show me some of those supernova remnants, you will find hundreds of pictures that look all pretty beautiful. And we see them also. So we see these supernovae, we see them popping off in other galaxies as well, because they are so powerful. These are basically beacons that we can see throughout the whole universe, because they're so bright. If a supernova goes off in a faraway galaxy, we notice that. So it's kind of weird that sometimes one single star that explodes can be so bright that we can see it basically through the whole universe, across the whole universe.
So the remnants or everything that's exploding outward, is that like everything it touches? Is that like a path of devastation? Or if you're like far enough away, is that like a gravitational wave, or like what are the effects of that path? Yeah, so as I said, the largest amount of energy is carried away, 99% of that explosion energy is carried away by neutrinos. Neutrinos have that, for people who want to study them, have that annoying ability to go through everything without leaving a trace. In fact, there are probably billions of neutrinos going through you at this second, coming from the sun and other places in the universe. And by the end of your life, there may have been one interaction of a neutrino with you. Those neutrinos, they don't do very much at all. That's the nature of the beast of neutrinos. That means that 99% of the energy just dissipates in that form and is gone. But even that 1% is quite a lot. And yeah, if you're too close, I mean, if there's a planet around these stars, that planet will probably get completely disrupted and torn apart. But already at a distance of about 5 or 6 light years, the material itself will not harm anything anymore. It's more, one has to be a little careful because there are lots of X-rays and gamma rays, and so they of course are harmful wherever you are. So that, but other than that, no, it's not really anything that rips apart whole stars or so now. Because what you also have to remember always is that space is large. So one light year is already a very large distance, and if you dissipate all of that energy over a couple of light years, there's very little at each single location.
Well, if anyone wants to stick around and ask questions, I want to thank Stephan Frank again for tonight's presentation. And yes, please. And we hope that you'll come back. OSU Astronomy Department will be back on Thursday, July 18th at 7:30. And again, hopefully it will get dark. Well, we know it will get dark a little bit earlier, but hopefully the weather cooperates and we will have telescopes outside in July. Thank you all for coming.